In this video, we look at graphing rational functions. There are a few steps that we're going to follow. We don't necessarily have to do them in order. This is just one of the orders that we can do them in, although the first two steps are probably pretty important to do in order. So the first thing we want to do is to state any restrictions, to identify any restrictions on the domain of the function, and we do that so that we don't lose any of those restrictions. And you'll see as we go through what that might look like. We also want to simplify as much as possible and identify any holes that result from that simplification. Again, we'll go through an example so you can see that. We'll find the vertical asymptotes. And just a reminder, the way that we find vertical asymptotes is by setting the denominator equal to 0. Then we'll find the horizontal asymptotes. And the way we do that is to divide every term by the highest power of x in the entire equation. So that's something that's a little bit new, but we'll go through the process so you can see how that works. X and Y-intercepts will be helpful for graphing, and then looking at the end behavior. If we can do all 6 of those things, then we'll have a good sense of what the graphs are going to look like. Just a reminder that a hole happens when a factor can be divided out of the numerator and the denominator. So we'll have a look at some examples here. In fact, why don't we get started right away in an example, and then you can see what that looks like. All right, so we're going to start with a simple example here. We're going to sketch, I shouldn't say simple. It looks kind of complicated. So this is a rational function. It has a polynomial as a numerator, a polynomial in the denominator. So that fractional sort of look is what causes this to be a rational function. So our first goal here was to state any restrictions. In order to do that, we look at the denominator. And from the denominator, we determine what the restrictions are going to be. So from this, we can see that x cannot equal -1. If x is equal to -1, then that denominator is equal to 0, and we get division by 0, which isn't allowed. So we say that x cannot equal -1. So that's our restriction. We're going to simplify if we can. So notice here that this function's in factored form in the numerator, and there's only the one factor in the denominator. But notice that there's a multiplication of 2 factors in the numerator, and then we're dividing. So we can actually kind of split this out and say that x plus 1 divided by x plus 1 is equal to 1. So that leaves us with the function f at x equals x plus 2. That's all that's left. So this actually simplifies to a linear function. Now just a little bit of word of warning here is that when we divided out this x plus 1, this factor in the numerator and in the denominator, that creates a hole. So this generates a hole at x equals -1. We already knew that there was a restriction at x equals -1, and now we know that that restriction is going to result in a hole. So we're going to sketch this function f at x equals x plus 2. It will look like this. It's a straight line. It has a y-intercept of 2. Try to roughly get an approximation here. And it has a slope of 1. So we can go up 1, over 1, and that'll be our, let's try that again. That will be, hang on a second here. So we said that there's a y-intercept at 2, and the slope is equal to 1, so we can go up 1, over 1. We'll get a straight line that we could draw through those 2 points. Approximately. And that is what our function looks like. You know what, I'm actually not going to, I was going to use the straight line tool to give us a straight line, but that's not going to allow me to show the hole very well. So what I'm going to do is to draw the hole in here. So if our line looks like this, I thought I could do it as 2 lines, but I think that's going to be too challenging. So I'm just going to freehand this. And if this is -1, we've already determined that there's a hole at x equals -1. So I'm just going to take my eraser and just kind of draw a gap in there, and then we show the hole using an open circle. So that open circle just indicates that there's a hole there. So this is a function. It's a straight line. It does have a hole here at x equals 1. Sorry, that's supposed to be a straight line, but does have a hole there. That was a simple looking function. Sorry, not simple to start with, but once we simplified it, it was a straight line, but we did need to identify the hole there. No horizontal asymptotes in this case. We could find the x and the y-intercepts. I guess we found the y. If we wanted to find the x-intercept, we could set y equal to 0 and solve for x. So let's do that. So we've already determined that the y-intercept here is equal to 2, and we'll find the x-intercept. Probably don't need to do it for a straight line because you know what that looks like. So for the x-intercept, what we'll do is we'll set y, let's try that again, equal to 0 and solve for x. Take away 2 from both sides and we get x equals -2. So this function will have an x-intercept here at -2, and you can see my picture's not exactly to scale. And again, we don't need to worry so much about the end behavior here, and the reason for that is that there are no horizontal asymptotes, so this function is going to continue. So the end behavior is that as x approaches, I forgot my x in there, as x approaches infinity, y is also going to approach positive infinity, and as x approaches negative infinity, y approaches negative infinity. All right, so let's move on to a more challenging example, one that doesn't turn into a straight line when we simplify things. So here's a function right here, similar in nature, I guess. Let's go ahead and state the restrictions. So if we look here, we want to look at the denominator and what values of x are going to make that denominator equal to 0. So x cannot equal -1 and x cannot equal -5. So those are our restrictions. And now we can go ahead and simplify things. And when we simplify this, same sort of thing is present, or same sort of situation, pardon me, is present as we had last time, where we had a factor of x plus 1 in the numerator and the denominator. So the fact that we're able to divide those out is going to produce a whole. So I'm just going to jot that down here, so when we go to graph this, we don't forget that there is a whole, pardon me, at x equals -1. All right, the vertical asymptotes. So in order to find the vertical asymptotes, we want to set the denominator equal to 0. I'm just going to use VA for a short form for vertical asymptote. So the vertical asymptote here happens when the denominator is equal to 0. So maybe before we do this, let's just simplify this function entirely. And when we do that, we get that our function here, f at x, is equal to 2x plus 1 divided by x plus 5. So the vertical asymptote happens when the denominator is equal to 0. Well, if that's the case, let's set the denominator equal to 0. We can subtract 5 from both sides, and we get a vertical asymptote at x equals 5. Sorry, that's a -5. Let's see if we can fix that up. And I think maybe what we'll do is we'll just graph this as we go. Every little feature we find, we'll just create the graph. Hard to graph the whole until we have a good sense of what the function looks like, but we do know that there's a vertical asymptote at x equals -5. So I'll stick x equals -5 somewhere out here. Call it, let's say right about there. So I'm actually going to draw that vertical asymptote in. And there's only one vertical asymptote in this case. All right, so our next step in our series of steps was to find the horizontal asymptotes. Now this one's a little tricky at first, but once you get used to it and you get to see how it works, it might make a little sense. So if you remember back to the previous page, we said that in order to find the horizontal asymptote, we divide every term in our function, so every term in this function here, by the highest power of x. So look at this function, and what is the highest power of x in this function? Well, there are no squareds, there are no x squareds, no x cubes, and so on. The highest power of x is equal to x. So in this case, we're going to divide everything by x. And so that's going to look like this. So we'll take our 2x, the first term, and divide it by x. We'll take 1 and divide it by x. So again, we're dividing everything by x. And this gets a little bit messy in the sense that there are fractions within fractions, but that's okay. We'll clean that up pretty quickly. Now the goal of the horizontal asymptotes is to see what's happening way out in the positive, x direction and way out in the negative x direction. So really what we're going to do here is, I'll come back to that. Save that thought for a second, because we can simplify this part. Let's do this part first. So 2x divided by x, that's just equal to 2. X divided by x is equal to 1, so we'll jot that down. Now this is the hard part here. What's 1 divided by x? Well, again, we want to see what's happening when x gets really, really, really large. So what happens to 1 over x as x becomes infinitely large? So if x is 10, we get 1 over 10. If x is 100, we get 1 over 100, and so on. As x gets infinitely large, and here's the tricky part, this thing is going to go to 0. So 1 divided by x as x gets really large is going to approach 0. And the same is true down here. 5 divided by x as x gets really large, this thing is going to go to 0 as well. So we get 2 plus 0 over 1 plus 0, which just works out to 2. And that's a tough concept, that idea that x is getting really large. So think about subbing in a really big number, because for the horizontal asymptote, we want to see where's that function going as x gets really big in the negative direction and as it gets really big in the positive direction. So we start thinking about subbing in infinitely large numbers in there. So we get a horizontal asymptote at y equals 2. So again, I'm going to stick that in here approximately. Let's say y equals 2 is somewhere around here. And we'll just draw in that horizontal asymptote. All right, so we've got the horizontal asymptotes. I guess the next step was to find the x and the y-intercepts. In order to find, well, maybe the y-intercept would be really easy. I'll just jot this down over here maybe. In order to find the y-intercept, we set x equal to 0. And so we'll get, so remember our function was f of x is equal to 2 times x, and we said x is going to be 0 plus 1 divided by 0 for x plus 5. Oh, sorry, I just realized I made a typo. Fix that up. Said 1 and wrote 5. And we get 2 times 0 is 0 plus 1 is 1, and 0 plus 5 is 5, so we get 1/5. So the y-intercept is at 1/5. So less than 1, 1/5. Let's put it somewhere in about here. In fact, let's use a different color for that. Let's do this in red. So we get 1/5 right here. All right, and now let's find the x-intercept. And in order to do that, we will set y equal to 0 and solve. So we get 0 is equal to 2x plus 1 divided by x plus 5. Now this looks maybe tricky at first, but don't forget that 2x plus 1 divided by x plus 5 is just a fraction. This is a fraction. I mean, that's the whole goal here, is to look at how to graph these. Well, what's the only way that a fraction can equal 0? Well, the only way that a fraction can equal 0 is if the numerator is 0, so let's focus on the numerator. So 2x plus 1 is equal to 0. Solve the equation, subtract 1 from both sides, and then divide by 2, and we get x equals -1/2. So our x-intercept is x equals -1/2. Let's say it's somewhere over here. So without doing a whole lot more, I think we have a good sense of what's happening here. It looks like this function is as we head to the left, is going to get closer and closer to this vertical asymptote here. It can't cross the x-axis again, otherwise we would have found another x-intercept. So it has to come down. That's the only option. And then as we move from left to right, it's going to approach this horizontal asymptote and get closer and closer to that asymptote. Now, one of the steps here was to consider the end behavior. That was step 5 in our list of things to look for. When I say consider the end behavior, I'll see if I can squeeze that in down here. Look what happens to the function as x gets really large. So let's choose a large value for x. It doesn't even have to be that huge. What happens to this function as x equals 10? Well, let's substitute 10 in. So f at 10 is equal to 2 times 10 plus 1 more divided by, we said x was 2 plus 5. So what's that? That's 21 over 7. Let's just make sure I didn't make a mistake. Oh, you know what? I did make a mistake here. I subbed in 10 in the numerator, but only 2 in the denominator. Let's fix that up. Say something didn't quite look right here. So in the denominator, we should have an x plus 5. So x is 10 plus 5 more. So we get 21 over 15. Now, it doesn't really matter what that value is. All that really matters is I want to see, is it bigger than or smaller than 2? And if that answer is bigger than 2, then our graph would cross the horizontal asymptote and come down, back down and approach it. If it's less than 2, then we're going to stay below that horizontal asymptote. And if you wanted to check another value, you could check f at 100 if you want, just to make sure. But I'm pretty confident that's what's going to happen. And then we can do the same thing on the other side. So let's look at f at negative 10. So we'll get 2 times negative 10 plus 1 divided by x, which is negative 10 plus 5. And when we do that, negative 20 plus 1 is going to be negative 19 over negative 15. So we know that this number, again, is, in this case, it's actually, it looks like it's less than 2 as well, doesn't it? Let me just make sure we didn't make a mistake here. Negative 20 plus 1. Oh, yeah, this is a positive number. 10 plus 5. Negative 10 plus 5 is not negative 15. There's my mistake. Thought something didn't quite look right. That should be a negative 5. So we have 19 divided by 5. The answer is going to be positive. We know that that number is greater than 2. I don't know exactly what it is. Well, it's 19/5. If we really wanted to know, it's greater than 2, and that's what really matters. So that means that as this graph approaches our horizontal asymptote, it's going to do it from above because this number down here was bigger than 2. And then it has to get closer and closer and closer to the vertical asymptote. And we know that there's no more X-intercept, so it can't go down. It can't go down this way. Otherwise, there would be another X-intercept. So that's how we can graph that one. And then I guess we're pretty much done. We've checked, we've stated our restrictions. Oh, the one thing we missed was the hole. That's the one thing that we missed. So we know that there's a hole at x equals negative 1. Oh, that was right here, wasn't it? Let's see. The X-intercept was at negative 1/2. So our hole is going to be somewhere right in here at negative 1. And I'm just going to take an eraser and erase the line so it doesn't show. And then we can draw our open circle to indicate that hole. And again, this is just an approximation. That's at negative 1. So we've got the hole, we've got our vertical asymptote, our horizontal asymptote, our x and y intercepts. Typically with a graph like this, the x and y intercepts will give you a good sense of which way the graph is going to go. And then you can kind of play around with things from there. So that's how we can graph rational functions, provided they're factored for us. We'll talk a little bit more some other time about what happens if they're not factored. I think you can probably figure it out.